get what? Big D. Here's little d. Is the diameter of a little circle, and here's big D. Big D times L1 plus L2 plus L2, yeah. Now, as n gets larger and larger and larger, as we're chopping into more and more and more and finer pieces, the intuitive leap of faith is that these numbers, which are marching to the right, are getting closer and closer to a given number. This is the circumference. So this is getting as close as you like, within a trillionth, 100 trillionth, 100 trillion trillionth. Who has the names of those large numbers that Terry gave me? I said 100 centillionth. Okay, it's 10 to the 1 over 10 to the 34th or whatever. This is as close as you like to the circumference of the big circle, this sum. See, as you take more and more choppings, this sum is as close as you like to the circumference of the little circle. So that you can conclude that D times big C is equal to big D times little c. Or you can change the algebra around, and this says that C over big D, this is the intuitive argument, this is the argument that C over big D is equal to little c over little d. So it doesn't depend on the size of the circle. It's some universal number which is out there. Now, remember, the Platonists believed that mathematics existed independent of mankind. That if the universe ended and there was somehow another Big Bang and another universe, pi would pop up again. Or, they did. You may not.
Well, physicists today don't.
Okay. Okay. Well, okay. So anyway, this is the philosophy. So therefore, there's some universal constant which we define to be what? Pi. And then the question is, what is it? Now, it was only in the 19th century that we found out that pi was irrational. It's not a fraction. Not only is it not irrational, square root of 2 is not a bad irrational, because it's the root of an algebraic equation with integer coefficients. The square root of 2 is such a nice thing. Look, can you get a better equation than that isn't linear? X squared minus 2 equals 0. The solution is x equal what? Yeah, that's an integer. Everybody knows, even the stone men knew 2. 1, they knew 1. They simply didn't write down x squared minus 2 equals 0. But the solution is, we forget negatives because they don't exist at this point. They get x equals the square root of 2. The problem is that pi is not the root of any simple equation like that with integer coefficients. It's not an easy result. So it's badly irrational. You could call it. Pi is badly irrational. Okay. So how we have time now? So now that we have this, we are really in a position to derive the formula for the area of the circle. We're all ready. It's now a trivial leap. But we need now a slightly different construction here. So what I want to do now is get rid of the big circle. I don't need the big circle anymore. I can get rid of it. So now, what do I want to do? Well, the idea is going to be fairly obvious. I want to chop up I want to chop up the circle again into a lot of parts. 2 to the n, 8, 16. Now, here's the intuitive leap of faith if you want to calculate the area of a circle. First, we we know how to calculate the area of a triangle. That was trivial for the Greeks. It's trivial. Requires no leap of faith, for a great mind is obvious. Okay, now, look at these triangles here. I can't even draw them this so little. Now, implicit in this, by the way, is another subtle idea that I should point out here before I forget. A very deep idea, which is the basis of all of calculus. You have to have a fundamental philosophy when you're dealing with subtleties of what is a curve and what is a surface. By the way, the actual modern definition of surface is so difficult. It had a long history of development already from the 15th century to this century. The modern definition of a surface actually was not written down until 1912. It was written down in a book by a German mathematician by the name of Hermann Weyl. Die Idee der Riemanischen Fläche, the idea of Riemann surfaces. So, okay, that's the idea of a surface. So these are really subtle things that people have struggled with. Okay, but the intuitive idea of what a curve is, which helps, in fact, ultimately define what a surface is, that a curve is intuitively, if you were very, just like the surface of the earth, if you were a very tiny creature living on this curve, let's say a microbe, a virus, and you lived on this circle, and you were talking to your other microbes, you would conclude, unless there was a genius around, that the world you lived in was what? Straight. Was straight. So, in fact, included in that simple idea and in that classical mistake of what the conclusion that people made about the shape of the earth is, in fact, in that mistake lies a foundation of all of modern ideas of what a curve and a surface is that infinitesimally, as you get smaller and smaller and smaller, curves look like what? Lines, straight lines. Surfaces look like planes. And you have to make that precise. So, but again, as I tell you, the roots of all these ideas were in ancient Greece. You only had to make sense of it. Okay. Now, so, therefore, intuitively, this little piece of the pizza is actually a triangle. Not exactly. So, let's now compute the area of this triangle. We know the area of this triangle. It's 1/2 the base times the height. The height is little r. I derived that for you, right? So we know that the area of the first triangle is 1/2 the base. Area of first triangle, 1/2 the base. What is the base? The base is, I call it little L1 times the height, which is, hey, thank God it's always the same. It's the radius. So the area of the second one is what? L2 times r plus 1/2 L3 times r, and so on, plus L3 times r, plus dot, 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 1/2 L to the 2 n, or L8, or whatever, times r. Now I can factor out 1/2 r. So this is the sum of the areas of the triangle. Sum of areas of triangle. Equals. Now, so this is 1/2 r times L1 plus L2 plus dot, 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 L2 to the n. Now, second leap of faith. The first leap of faith was that as we take more and more choppings, the sum of the lengths of these lines is going to get closer and closer to the circumference. They're actually moving to the right. So they got to get close to something. If I'm moving to the right, there's got to be some limiting thing there. I can't, I can't continue to move to the right without getting closer and closer to some limiting point. Oh, there it is. Okay.
Tony.
So now again,
Tony.
these things, yeah.
Don't you need some number that you know that it doesn't go below? Like you need some.
Well, we do have that here.
Yeah.